Under this topic, we'll compare conductors and semiconductors. So, what are conductors? We know that very well. And what are semiconductors? We know that as well. So, before comparing them, let's revise the concept that what are conductors and semiconductors, and after that, we'll compare them. So, what are conductors? And as we know that the metals are the best examples for conductors. So, we'll consider metals to understand because metals conduct heat and electricity completely, and metals have loosely bound electrons. Those are also known as valence electrons. If we'll try to define what are valence electrons are the electrons in the outermost orbits, right? Now, valence electrons are loosely bound electrons. Why it is like that? Because we have nucleus at the center, then we have orbits. So as we move farther from the nucleus, or the distance between the particular orbit and nucleus increases, the force, the strongness of force decreases, force becomes weaker. So if the orbit is far from the nucleus, that means electrons, those are revolving in that orbit, will be loosely bound with the nucleus. Electrons have negative charge, nucleus has positive charge. So negative force is force of attraction, but the force of attraction decreases as the distance increases because it is inversely proportional to square of distance, right? So in metal, atoms are close to each other and valence electrons from each atom get confused. So in metals, the structure of metal is like this. Atoms are close to each other. These are atoms and each atom will have nucleus and orbits of electron. So in this case what happens is, suppose one electron is revolving in this orbit. So during its revolution the electron can get confused at this place, like if it is revolving in this orbit or this orbit. So electrons can start revolving in the orbit of any other atom because of that confusion. Now, and why? Because they are very close. Atoms are very close to each other in metals. Now, they now belong to the metal as the whole because they have forgot their path and they've started revolving in any other orbit and orbit of any other atom. So we'll say that those electrons doesn't belong to any particular atom, but they belong to metal as whole because they can move from one place to another inside the metal. Now, positive ions which are tightly bound and in fixed positions can only oscillate around their equilibrium position. So positive ions, when electrons will leave, one electron will leave the atom, that atom will acquire positive charge. So we'll consider that as positive ion. So they can only oscillate between their equilibrium position from a positive background. Now, at the all the homeless electrons, so electrons we were talking about when they'll get confused and they'll start revolving in any other orbit. So those electrons are called free electrons or sea of electrons, and they are homeless. So we'll use the term free electrons or sea of electrons. Now, so this is the sea of electron. These are the atoms and these are the electrons. So these are the positive ions we can say, and electrons can revolve here and there throughout the metal. Now, what are semiconductors? Semiconductors are the materials that can be made to behave sometimes as insulators, sometimes as conductors. So when they behave as insulators, below room temperature. As the temperature increases and it reaches above room temperature, they'll start conducting. Now, silicon and germanium are the best examples for semiconductors. these days we have compound, so these are element semiconductors. We have some compound semiconductors as well, like gallium arsenide and all. In pure crystalline form, they are insulators. But if replaced, so in pure crystalline form means we have silicon, silicon, silicon in one crystal, everywhere silicon, silicon, or germanium, germanium, germanium. Like, right? But if we replace one atom in 10 million with an impurity atom, so any one atom from a crystal will replace with one impurity atom of either third group or fifth group, because silicon and germanium both are from fourth groups. So when we'll replace any one atom out of 10 million atoms from any other atom, so we'll replace, like the structure will be like this: silicon, 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 and here we'll have either boron or phosphorus or any other element. In that case, their conductivity increases and they'll start behaving as um, conductors, right? So they'll become excellent conductor after that. So it depends that if we'll mix the impurity of third group, they'll become p-type semiconductor, and if we'll mix the impurity of fifth group, they'll become n-type. So we have p type and n-type semiconductors. Now, all the semiconductor devices like IC, diodes, transistors, they all are made up of semiconductors, right? Now, what is the difference? Difference is semiconductors doesn't conduct below room temperature, but conductors can conduct below room temperature as well. And if we'll talk about their energy level diagrams, so this is for conductors. So this is for conductors and this is for semiconductor, right? So this is E1 ground energy state, this is E2 excited energy state here as well. So all the atoms lie in ground energy state, and when they absorb the energy of delta E, which is E2 minus E1, delta E amount of energy, E2 minus E1, which means difference between these two states. So when they'll absorb that much amount of energy, they'll jump back into uh, excited energy state. And there's another name. This is known as valence band, and this is known as conduction band. So any material can conduct when it has some electrons in its conduction band. Otherwise, it cannot conduct. So in case of conductors, in some of the metals or conductors, valence band and conduction bands are like this. They are overlapped, right? So no need to provide any energy, no need to raise the temperature, increase the temperature. They, without doing anything, they can freely move from valence band to conduction band because both bands are overlapped in case of conductors or metals. But in case of semiconductors, there is some gap between valence band and conduction band. So we need to provide some energy from outside so that atoms can jump from valence band to electrons can jump from valence band to conduction band. This energy gap is not that much high, it is less than 3 electron volt. Like in case of insulators, this band gap, the distance between valence band and conduction band is too high, so that electrons can never jump from valence band to conduction band. That is why insulators doesn't conduct heat and electricity. So here it is less than 3 electron volt. To be more precise, in case of silicon, because we have studied silicon and germanium, are the two best examples. So in case of silicon, the band gap is 1.1 electron volt, and in case of germanium, it is zero point 0.7 electron volts. So that is the difference between conductors and semiconductors. So this is all about their comparison. Thank you.